So we saw that the operating principle of induction motor then is very much comparable with that of a transformer, in the sense that transformer is a single phase device. It has got two windings, primary and secondary. When we give supply to the primary, a flux is set up. That mutual flux will link the secondary, and there will be EMF induced in it. If you connect a load across the secondary, it will get power. So the power is transferred from the primary to the secondary by induction. Similarly, in an induction motor, we have got two windings, two sets of windings, a three-phase regular three-phase winding on the stator, to which we give the three-phase supply. So this is the primary winding. And on the rotor, we have again a winding, either a cage winding or a regular three-phase winding. If it is a cage winding, it is short circuit on itself. And if it is a three-phase winding, it is short-circuited externally through brush and slip rings. So, what happens when we give supply to the primary? It is a three-phase winding. So, when three-phase winding is fed from a three-phase supply, it will create a rotating magnetic field of constant amplitude. So, as initially, when the rotor is at rest, the rotating magnetic field is rotating with respect to the rotor at a speed we call the synchronous speed. The speed depends on the supply frequency and the number of poles. So, as the rotating magnetic field is moving with respect to the stationary rotor, so the flux linkage of the rotor conductor changes with time. So, there we, according to Faraday's law, as the flux linkage changes, so there will be EMF induced in the rotor conductors. Now, as the rotor winding is shorted, so there will be current flowing. Now, this current and the flux interact to produce a torque. Basically, the torque will be produced in such a direction that it opposes the cause. The cause is a relative motion between the rotating magnetic field and the stationary rotor. So the rotor will start rotating in the direction of the magnetic field such that the speed difference reduces. So initially, when the electrical quantities are induced in the rotor, those are at supply frequency, because that the frequency will depend on the relative speed between the rotating magnetic field and the rotor. Now, as the rotor starts gaining speed, so the relative speed between the rotating magnetic field and the rotor will start decreasing. So now the EMF will be induced in the rotor, but at some other frequency, which is basically the difference between the supply, which will be proportional to the speed difference between the synchronous speed and the rotor speed. What we call is the slip speed. And we have seen that if the supply frequency is F, then at any slip S, slip is defined as the synchronous speed minus rotor speed divided by the synchronous speed. So it is a pure number. If the motor is rotating at with the slip S, then the rotor quantities have a frequency of SA. So initially, EMF which was induced in the rotor, if we define it as, say, E2, which will be proportional, which E1 and E2 magnitudes will be depending on the number of turns. So both will be, E1 and E2 will be at supply frequency initially, but as the rotor's speed increases, so frequency will change. So now at sleep S, it will be AC2. Now this phasor, however, it has been changed to purity ratio, so it is E1 basically. It is multiplied by the turns ratio. So magnitude of the induced EMF changes. So also the frequency of the induced EMF changes as the rotor speeds up. Now, so this was the phasor diagram, what we have explained earlier. That is similar to the. It looks similar to that of the transformer. That is, we start with the mutual flux phi as the reference. So if phi is as a reference to if there will be a current component, this component of current, which is in phase with the flux, producing the flux. Now, the alternating magnetic flux is associated with hysteresis and eddy current loss, so which is an active power. So there should be actually the current cannot be in phase with the flux. There should be some component which is in phase with the induced EMF E1, which will produce the supply the core losses. So actual no current is this. Actual magnetizing current is this. That is the magnetizing current, but the core plus the core loss. So this also we have studied in case of transformer. That is as the BH curve is non-linear, so and there is a hysteresis loop, so we know there will be an angle between this current and the flux, which is the hysteresis angle. So this is the total magnetizing current requirement. That is the magnetizing current plus the core loss current. Now, actually, it's this is basically I0. We can also define this by I0 because these nomenclatures might differ from book to book. This phasor I have taken from SAY. They have shown it as IM. In some book, you can see that this component is IM, this is IC, and this is I0. That is okay, but whichever concept you follow the same one and explain the phasors. So besides this, what will be the other current? Now in the secondary under no load condition, the sleep is very small. So basically the current which is flowing in the short circuited secondary is very small, so it is negligible. So if we neglect that component, so this is the no load current. Now what happens as we increase the load, so the rotor will slow down. So as the rotor slows down, so the sleep will increase. So as sleep will increase, this current magnitude, this secondary induced EMF is SE1. Now the current magnitude, this EMF divided by the secondary impedance will increase. So, and this secondary current will have a reflection in the primary. So this is I2 dash. So this component reflection is minus I2 dash. So here our stator current will be this current plus this I2 minus I2 dash. So this is I1. Now in the stator circuit, what we have the induced EMF E1, and due to I1 there will be I1 R1 drop, I1 X1 drop. So your supply voltage V1 should be summation of these three phases. Now the stator input the input power is V1 I1 cos phi 1. So I1 has components. This is I2 dashed. So this component of current will supply the core losses, and if we consider this voltage, this V1 these three are the components. Now this I1 R1 into I1, that will give you the I1 square R1, the copper loss. Now I1 X1 I1, that is perpendicular, so there will be no, that is no active power corresponding to this. Beside this, we will have minus I1 into this component, loss component, that will give the core loss, and the rest, that is this current and P1 and the angle between these two. Basically, this angle will be same as phi 2, because this I2 is actually, we can write, draw it here also. So that angle is phi 2. So that is the power which is transferred to the rotor. Now, and in the rotor circuit, so this is I2 dashed, R2 dashed. So this rotor circuit voltage has two components, this component and this component. So that rotor circuit voltage into current, that is into the power factor angle, that is the rotor circuit power equal to the rotor circuit power. Now this component I2 dash R2 dash into I2 dash, that will be I2 dash square R2 dash, that is the copper loss. So the rest will be the mechanical power. And we have seen that it has a relationship with the slip, that is P2. The secondary power is I minus I2 dash, I minus E1 minus I2 dash cos phi 2 is I1, I2 dash cos phi 2 is 1 by S, E2 dash I2 dash cos phi 2, because we are replacing E1 by this 1 by S, E2 dash. So our this component, that is E1 I2 dash cos phi 2, this is I2 dash square R2 dashed. Hence, this is equal to I2 dash square R2 dashed is equal to this expression. So our P2 is equal to I2 dashed square R2 dashed by S. So I2 dash square R2 dashed is equal to S into P2. Now I2 dash square R2 dashed is basically the copper loss of the secondary. So secondary copper loss is equal to S into P2, where P2 is the power transferred to the secondary across the air gap. It is also defined as the air gap power. So if P2 is the total power transfer, so that minus the loss, that is 1 minus SP2, is the power which is mechanically transferred, which is converted to mechanical form. This is not reflected in the phasor diagram, because that is power is converted to mechanical form. So PM is equal to 1 minus S into P2. So it has a typical relationship, that is P2, the air gap power or secondary input power, is to the mechanical power developed is to the rotor copper loss. Rotor copper loss per phase, because if we have 3 phase, it will multiply by 3. All quantities are per phase quantities. Is equal to 1 is to 1 minus S is to S. Now this relationship, that is these 3 powers should be in this ratio. This is independent of whatever assumptions we have made. That is, we have made certain assumptions that the mutual flux remains constant, and we have seen that there will be slight variation and some other things. So even it is independent of that assumption. So this relationship is always true. And we have got the torque also. Torque will be developed. Torque is power, the mechanical power developed by twice pi n. So this was shown to be equal to P2 by twice pi ns, where P2 is the air gap power transferred to the rotor across the air gap divided by the synchronous speed. So torque is sometimes defined as P2 synchronous watt. Also, that is by definition, synchronous watt is the torque which at the synchronous speed of the machine will develop a power of 1 watt. Now next we will go to the equivalence circuit. Now equivalence circuit, that is, our aim is to represent the motor by a circuit consisting of passive element like resistance, inductance, etc., so that that circuit will reflect the performance of the motor. So that circuit should have the same phasor diagram as we have shown in this figure. So whatever we have studied, we have seen that if, these things should hold good. That is, E1 by E2 is equal to A, the turns ratio. Your turns ratio will be the winding factor into number of turns, that is Kw1 into T1 by Kw2 by into T2. So effective turns. So similarly, I2 dashed by I2 is equal to 1 by N. Second, the magnetizing component of the stator current lags the induced EMF by 90 degrees. So the magnetizing current, what is considered is a magnetizing component, that is this component which is lagging by 90 degrees. And the induction machine has not only changes voltage and current levels, the frequency also is transformed. And so we have seen that it is called the generalized transformer. That is, in case of transformer, the voltage and current level changes in the secondary circuit, and in case of induction motor, in the secondary circuit, voltage, current level as well as frequency changes, because the absolute frequency of the secondary is something different. It is the slip frequency. The circuit model of the induction motor can now be drawn similar to that in case of transformer. Now this it is normally the turns ratio is A:1. Now we can change this to 1:1 ratio. In the same way, we have transferred the secondary quantities to the primary voltage level in case of transformers. That is, the secondary impedances should multiply by turns ratio square. So Z2 dashed will be A square R2 plus JS, because the impedance is JS X2. So JS A square into X2. So this is R2 dash plus JS X2 dashed. Now the current, secondary current I2 dashed will be the voltage induced divided by the impedance. So if we take this S2 dashed outside, so inside we will have R2 dashed SS square plus X2 dash square. Now when we take it outside, it is a over root over, so it will be S. So this S cancelled out. So we have the equation E1 by root over of R2 dash square SS square plus X2 dash. So look into this equation. Here it is frequency is SF, but in this equation you can see that we have by manipulation we have changed the circuit. Here the circuit was here, this inductance portion was variable, and both this induced EMF was also variable, but we have by manipulation we have got this equation which will give the same magnitude of current. But here you can see that this is basically at the supply frequency, only that now it is a variable resistance circuit. As sleep changes, this resistance, effective resistance of the rotor will change. Now, so our first thing is that when we are developing the phasor diagram, this is the first stage. That is, our induction motor is similar to the transformer. So from that point of view, we develop the equivalent circuit. So in the primary, what we will have primary resistance R1, primary reactance X1, and in the primary there is a magnetizing current flowing. So neglecting, not considering the core loss component of current, if you only consider the magnetizing current, so it is lagging E1 by 90 degrees. So this is a pure inductance. So this is a magnetizing reactance in parallel, and this is the primary coil. So this is E1. Now this is coupled with the secondary. In the secondary, the EMF induced is AC2. The inductance is variable, SX2, and we have resistance R2, and it is shorted. Now in this this one we can call as an ideal generalized transformer. This is an ideal transformer because we have taken the resistance and inductances, everything outside the as lump parameter outside this. So this portion is ideal. That is it is that on these two coils are magnetically coupled, no resistance, no inductance. Here also inductance and resistance taken outside. So this is an ideal transformer, and it is a generalized transformer because the frequency levels also has changed. This is frequency F and this is frequency SA. Now next one, that we can transfer the secondary. This is ratio is A:1. So we can transfer is2 into a transformer with ratio 1:1. That is, we can refer the secondary quantities to the primary side, so that the power so we have the same way we have done for the transformer. Here we multiply the impedances by A square, both resistance and inductance, and the EMF by A, and divide the current by A for the transistor. So we have this circuit where these are the primary resistance and inductance. This is secondary inductance and resistance refer to the primary voltage level, and this is again the ideal transformer, but the ratio is 1:1. This is still a generalized transformer. So this was the stator equivalence circuit. This was the rotor equivalence circuit. So the rotor in initial these rotor quantities at rotor frequency, that is SF. Now first what we do, we convert it to the turns ratio, that is A:1, we convert it to 1:1. So this impedance is multiplied by A square, current is divided by A, and the voltage is multiplied by A. Now this circuit is this one. So if we just readjust, we have seen in this equation that if these two equation, you see that here I have taken S square outside, so this equation reduces to this. Now the difference, you can see that this equation, this quantity is as frequency SF, but this equation, this quantity is at frequency F, only it is a variable resistance. So this is the corresponding equivalent circuit for the rotor. So if we replace this circuit by this, because these two, though the turns ratio is 1:1, we cannot connect because they are at different frequency. So if we replace it here, so we got this circuit. So here we see that stator and rotor frequencies are same, and this is also 1:1, so we can connect, and this is the equivalent circuit. Now here, however, we have not considered the core loss resistance. which will represent the core loss, because core loss is not reflected here. So for that we can add this resistance here. But in case of induction motor, normally what we do, as if we keep the voltage and frequency constant, core loss is constant. So to make the calculation easier, normally we consider this circuit. After solving, whatever developed power we get, from that the core loss is subtracted to get the actual mechanical power developed. So this circuit, this R2 by S can be divided in we can give R2 here, R2 dashed here, and the rest here. So this resistance, which is variable, will represent the mechanical power, and this is the rotor, represent the rotor copper loss. Now, as in case of transformer, here also we can develop a approximate circuit. Now here, one thing, remember that though I have just by manipulation converted it to frequency F, but actually if you think from the point of view physically, what happens, the magnetic field which is created by the rotor current will rotate with respect to the rotor conductor corresponding to a speed corresponding to the rotor frequency. So what the stator conductors will see, the rotating magnetic field will rotate with respect to the stator conductor. The speed will be the speed of the rotating magnetic field with respect to the rotor conductor plus the speed of the rotor. So that will be again ns. So whatever the frequency of the rotor, actually all the quantities when reflected on the primary side will appear at supply frequency. So there is no that is nothing wrong by representing this circuit, by replacing this circuit by this one. Basically quantities will reflect at supply frequency. So if we shift the shunt branch to the input side, we will get this one. This is the approximate equivalence circuit. But however, here in induction motor, as there is a air gap, we have seen that the magnetizing current requirement is quite high. The no load current is approximately 30 to 50% of the full load rated current. So if we shift the shunt branch to the input side, the error introduced is considerable. But sometimes in some operation calculation, if it is done for ease of calculation. So this is the equivalence circuit. So next year we will see how we can determine this equivalence circuit. In case that tests are also same. That is, in case of transformer, we have is derive this equivalence circuit from no load and short circuit test data. Here also we perform two tests. One is the no load test, open circuit no load test, and other is the block rotor test. So from these two test data, we can determine the parameters. So next class we will take on next Tuesday. Okay.